Alrighty, welcome to Michael Brand's Data Harmonization Talk. Michael is CEO and co-founder of Dynizer, a technology company which blends structured and unstructured data in the same environment. Michael has redefined the way massive quantities of disparate data are created and stored in very diverse formats. So welcome, Michael.
Hi, Steve.
Hi.
Okay, so maybe to get started, as an introduction, I could say that I might most probably be the only non-engineer in presenting at this conference. So I hope that my perspective on data will bring you something original. If you would like to interrupt me for question whatsoever, please feel free. I enjoy interaction. So basically, modeling. You're all I think, in the field of data modeling, what have you. And let's have a look at what usually is done. Typically, modeling is considered an engineering problem. People, they get a question from business users whatsoever, and they know there is data around, and they try and come up with a model that basically is capable of answering the problem or the question asked by the non-technical users in a company or an organization. Typically, if people talk about data modeling, what is taken into consideration is structured data only. Well, we as more technical people, we understand that there is structured and unstructured data. If I have to explain that to my wife, who's not dumb at all, for her, that distinction doesn't make sense. She has information, she has data, and whether it comes from a document or whether it is in a database or in her email, she doesn't care. So that's already in data modeling. We're doing something that only works for part of the data. And typically you create the model first. Before you do any data, before you put any data into the model, you need to fully create your model, because otherwise, where are you going to put the data? Because pretty much the meaning of the data and the use you're going to make of the data is determined by its position in the data model. And so, as said in the beginning, typically what happens is that a model is made to answer specific questions. And unfortunately, in a lot of cases, what you see is that when the data is modeled and people find answers to the questions, then the conclusion very often is that the questions weren't the ones that were accurate. And then you have to restart. And if you are a model builder and you are a data architect, that's job security, but maybe it's not the ideal way of getting the data done. And typically, a data model is produced very often to people that do not do the business, but that are technicians. What I would like to talk you through today is what I would call something more semantic and evolutive. Why? Because I think it is possible, if you think about data and modeling in a slightly different way, to basically model the data in a much more simple way, to not do it all up front, and to create a model that accommodates not only structured data, but also unstructured data. And that it is a model that you can start with very small and simple, and that you can extend, or that extends itself depending on the kind of data that you add to it, so that it remains up to date. And basically what I'm interested in is to have a model that doesn't only fit questions that you knew up front, but that is generic, that is not made in function of specific questions. And that basically it helps to use the data as you need it. And part of the evolution in the model can be automated. Not everything, but big parts of it can be automated. And let me talk you through a number of concepts that come into that way of working. Because if we start from what we all know, and these are very, very simplified table models, because typically you will find a bunch of ideas. I left all that out because the only thing I'm interested in here is actually the value data. Let's say that we have two systems and they both have a customer table. And what you see is that the name of the table is the same, but the content of the table is partially the same, partially different, because there is different properties or different columns in each table. Well, this brings us already to a number of things whenever you're trying to create a data model that integrates the data from these two systems, brings you some problems. Because it says, the first thing it says is that not every table in every system that is called customer has the same properties. Well, nothing very special, but when you want to integrate data, that immediately can lead to consolidation problems, to quality problems, what have you. So at a more generic level, what you can say about this is that one of the fundamental problems I have as a linguist with data modeling is the data modeling is basically the one who creates the model is God in his own environment, because in the model, he decides what the entities are and what the properties or the columns of each entity are. There is no generic principle, because the value of every entity, the name of every entity, the meaning of every entity is limited to the model in which it was created. So if you have to combine data from different models, there is no automatic interchangeability, because you don't know what it means. And that is also partially the problem when you talk language, because you have synonyms, but two words never are exact synonyms. They have a big part of the meaning that is the same, some parts of the meaning that are not the same. That is also in translation. So there is quite a bit of, funnily enough, let's say, similarity between what happens in language in translation and what happens with data. And basically, what is that? What happens? Well, basically, the main problem I see is that data models, they are ideographic models. This is something in linguistics we distinguish between ideographic and letter-based writing. And basically, Chinese is the biggest example of ideographic writing, which means every concept, every meaningful word has its own symbol. So there is basically one symbol, one character per idea, which means that you have thousands and thousands of characters. And the poor little Chinese kid that needs to learn to read and to write, he has to know at least 4,000 characters because before he can decently read a newspaper. And new concepts require new characters. With the speed at which language and society evolve at this point in time, even the Chinese have difficulties in keeping up. So they are now developing alternative systems to write. Well, basically, this is what we do in data modeling. Every time people create a model, they start from scratch, they invent their own symbols and their own relationships between the symbols. And you can have, well, take an SAP system. I wouldn't know how many thousands of tables are in there, but they're all let's say, arbitrarily chosen. If you look at what we do in Western European languages, we don't do that. We work with letters, let's say 26 in most Western European languages. And letters can be combined into words, and words into sentences, and that's what creates meaning. So instead of having to learn 4,000 characters, our kids, typically when they go to first class in basic school, after the first day, they come out and they can read and write their own name, which makes them very proud. Typically, why is that? Because we work with abstracted symbols. There is an abstraction between the sound and the meaning, and the combination of sounds and the complex meaning. Basically, what would it be nice that how nice would it be if we can actually change ideographic way of working for data models into something that looks more as to what we do with Western writing. Letters, we don't have, well, we have that in data in strings, of course, but basically we could limit the endless variety in entities if we would work with some kind of abstraction. The other part is, if we could come up with some abstraction like we have letters, then we could create our entities based on the same basic elements, which would make them more exchangeable. And we would have a more complex mechanism to introduce some kind of context, because within the same word, letters can be read differently. So the interpretation of something that is generic can be context specific. I don't know of any data and modeling environment at this point in time that allows you to define microcontext. So basically, how could we do that? If we could come up to with some abstraction, we could combine things in a more easy way, and we would not have the problem that things have the same name, but that they are not the same. Also, we would not have to deal with an infinity of entity definitions like in Chinese characters. We still could have an infinity of entities, but they would be constructed by the same basic building blocks, which would make them, to a certain extent, relatable in a more easy way. And basically, we would also reduce the dimensional problem, because it's a different thing to work with 26 letters and to learn and write 26 letters than to have to learn and write 4,000 characters. And basically, well, the combination of different models could be much more easy. If you can read Western characters, you basically can read quite a set of languages. If you know Chinese, the set of languages you can read is rather limited. If you are lucky, you can read part of Japanese, maybe a bit of Taiwanese, well, fair bit of Taiwanese, but that's about it. So if we could do something like we do with letters, if we could do something that allows us not only to model structured data, but also to model unstructured data in the same way, well, then it would also be nice that we can not predefine everything up front, but what we can use the system that uses some kind of abstraction to get things connected, that you don't have to think about all the connections up front. Well, let's look into how that could be done. Because if we can manage to do that, we can be interchangeable, we can have multiple contexts within the same model, and we can have an automated set of links discovered by the system without us having to think about everything up front. Basically, how could that happen? Well, that could happen by a very simple thing. And the simple thing is an abstraction that we know in philosophy and in linguistics since about 5,000 years. And that's basically that everything in language can be characterized as a member of one of four categories. It can be a who, it can be a what, it can be a where, and it can be a when. This typically is what in the policing world is called the event model, what in the journalistic world is called the story canvas, and then basically to make the story interesting for readers, you have the process categories why and how, because why and how are not data categories, they are process categories. And so everything that we encounter in our universe falls into one of those four categories. You can say, okay, but that's very abstract, you will have a lot of what? Yes, but now comes the interesting part. Because if we take our two different customer tables and we would model them with an abstract layer on top, then we could redefine the two systems and would combine the data. The nice part is that we have the abstract label for the first name that relates to a person, so that's a who. The last name relates also to a person, so that's a who. A city, that's a place, so that's a where. And basically, within the action is customer, I know that the first who in my column list will be of the label first name. And that first name label is only valid within the action, within the context is customer. So you could think about is customer as some kind of a flexible table. And within that table, the extra labels that we add to who, what, where, and when, they are only valid within that context. So they are not valid throughout the complete model. And that allows us to basically start with a very simple model where we first identify, if we have data coming from different structured systems, what the who, the what, the where, the when columns are in the data system. And then we can go more refined, more specific by adding labels or by adding new combinations of the same data that we give another context name, that we give another action name. The nice part is what we can do on top of that is basically that every data element we have We only have to store it once as a member of its category. So if we have the name Peter as a who, we have to store Peter only once. We give it a unique ID, and we can reuse it as many times as we want in different actions with different labels. The value will not have to be copied. You can just refer to it by its ID, which gives you a very small footprint system, and which allows you also, whenever you have conflicting elements from different databases about the same person, or whether you have to figure out whether the information is linked to the same name, but whether it is one or more people, you can use the links to actually find out without having to duplicate the data. That works for structured data, but it also works for unstructured data. Because strangely enough, if you look at sentences, then also sentences are built up mainly by out of elements in the who, what, where, when space. Well, that's normal because language is the most efficient way for people to actually exchange data, exchange information. So if you split this sentence, and that's not rocket science, then basically you can do a number of techniques to actually identify which elements refers to a point in time, which to a person, which to a place, which to an object or a what. And you see appearing a name action. Well, basically that's the context. That's typically in a sentence, the verb is what holds the information together. And here is our formal system, because we can transform the sentence into an action where we basically combine the who, the whats, the wheres, and the whens that we find in that sentence. And so the information that comes from sentences with the same context meaning, so if we have another kind of sentence taking as a context attend, we can group that information and we have it all together. But this structure is pretty easy because when I have in my customer table information about a Michael or a Paul, I can connect it. Whether that's then the same Michael or Paul, it's the links to other parts of my data that will tell me. And so instead of upfront defining, for example, what the best way is statistically to figure out if something belongs to a person or not, we can do it at query time based on the number of links that something has to another type of who, what, where element in a specific context. So basically, text or structured data, we build them into the same formal structure. And the nice part is, this is a table structure, and you can query it by using SQL because you have rows and columns and a table name. And if you have labels, you can even have a much more refined. So you can actually query the system at the level of the abstract labels, or of the abstract who, what, where, when categories, or you can actually query it by using the labels that you associate with these in specific actions, which gives you also the possibility to write semantically very complex queries in an easy way. How does that happen? How do we see the links? Because, well, transforming unstructured text into this structure, applying this structure to multiple tables in multiple databases, it's not rocket science. But the nice part is that if you do that with multiple pieces of information, and you have the who, what, where, when overlays, you can see where the crossroads are. And this is pretty much like a graph database works. But in a typical graph database, you don't have the degree of abstraction that is generic with the who, what, where, when. You have abstractions that are defined by the modeler. So just as you have the entities chosen by the modeler that puts himself in the place of God in the model. Here, the who, what, where, when is generic and allows you to actually get the connections. And so if two elements occur in the same context, of course, you will have direct connections. But if two elements are indirectly linked, because there is a direct link and then there is some distance, then basically you can also figure out the indirect links. And so you can have specific relationships, the ones you would typically predefine in your relational model, but you can also have what you would more see as a correlation, which is stuff occurring in the same context, where you can indirectly have access to via a query. And that you can align those by using joins if you know the specific context. So that's a way of working that allows you to build models in quite an easy and fast way. And it allows you to basically also make sure that a model can grow. Because once you have a table mapped in a relational system, well, the mapping remains the same. If you want to add a new table, you just need to make sure that you associate it with the appropriate who, what, where, when labels, and then it will be added to the system. And whenever there is an overlap at the elements, at the data elements themselves, you will have a link that the system can use and that you in your query can use as a join item or just as a query element to bring stuff together. So storing data elements only once as a member of each category also makes sure that you have a small model and that whenever there is quality problems, because you have different associations with the same data element, for example, multiple date of births for the same person, you can actually signal that. And then you have to decide based on your other data, if you can, whether it's the same person or not, or which date is most likely the correct one. Automated integration of unstructured data, because we created as a part of our Dynizer, which is the solution that allows you to do what I showed you in the slides, and I will give you a demo in a couple of minutes. We use a number of very advanced natural language processing and AI techniques to basically cut up texts into the who, what, where, when, and the context, so that you can add it to a system, and I will show you how it works in a minute as well. And whenever there is an overlap, as seen in the diagram that I showed, then you basically have a link with the data. Where it comes from is no longer an issue. Is it structured? Is it unstructured? Does it come from a semi-structured fill-out form? It doesn't really matter, because it's all modeled as an action consisting of who, what, where, and when. And then basically the data model that builds itself is a data model that is not modeled and created to answer upfront questions, but you get the model that comes out of the data. It basically will also make sure that once you have a simple model, you don't have, for every new kind of question, you have to restart modeling effort. So you can make it, you can make the effort once and then reuse it. And another, let's say, nice thing is that you don't have to go over different environments to figure out where the structured data is, where the unstructured data is, and so on. And basically, the nice part is, once you load the data in, you can actually start to browse and explore your data without having to write any query. I will show you that as well. And basically, what that helps you in doing is you start with a very simple mapping of your existing data, then you explore, and if you see interesting links in your data, you can actually select that subset of your data pretty easily and create a more complex, more refined model for that part of your data, so that you can show it in a more complex dashboard, or that you can do further analytics on top of it. Basically, that's the theory. Let's now go into a couple of examples that show you how it works in practice. I need to switch a second to my browser, and let's just take the easy route. What I will show you here is basically, this is our web interface to what we call the Dynizer, which is our data modeling and data storage and data querying environment. And so you have the regular things. You can actually go through your model. You actually have metadata available. You can look at the data, or we call it DQL because it's SQL with some extra functions. You can have pipelines to add the data. you can train the models for analyzing unstructured data and so on. I'm not going to walk you through all these details at this point in time, but what I want to show you here is basically what we do with the Data Explorer. What is in this data environment? And let me click this away this bit. This is basically an environment that we just set up because typically our customers, and we work, for example, for the Belgian system of justice, we work for the Dutch police, we work for some banks, we work for social support services. They don't want us to share any data in demos because it's all very confidential data. And I will say something more about that in my next demo. But basically here, what we did is we got out on the internet, and there is a lot of publishers that share recipes, cooking recipes, in a very accessible format. There is a JSON structure defined for it, and well, there's actually multiple JSON structures, but the nice part is once you have the JSON structure, you can map it to the who, what, where, and when. Typically, recipes, that seems to be very, very simple information. But how are you going to offer access to the recipe? Is it by type of cuisine? Is it by ingredients? Is it by allergy? Is it by cooking time? Is it by complexity of cooking procedure? Is it by the chef cook that actually invented it? What have you? So there is plenty of possibilities. If what we just did was we looked into the recipes, and basically what you see typically in a recipe, there is a number of elements. There is the author, there is a duration, there is the number of portions, and what have you. So you have a very simple description. You have the nutrients, that's what comes in there, and then we made an analysis of the cooking instructions. And what you have here is what we call the Data Explorer. And this is just a tool. Whenever you want to browse the recipes, you can easily do so. You can say, oh, I'm interested in getting recipes from, for example, Chief John, who is some kind of an American television cook. And automatically you will drive into, because you see the screen has 4 quadrants. The who's, Chief John is a who, of course. Then you have the what's, which is basically, it can be the ingredients, it can be the number of servings, it can be allergy elements or cooking instructions. You have the cuisine, from which country is it, from which region is it, and strangely enough, with the times, what do you get? You get the cooking times and what have you. With this, you can pretty easily select, without even having to know which recipes are there. The numbers tell you how many recipes match your selection. So I can say, oh, Chief John, we're quite a lot of people today, so I want 6 servings. I don't want to spend too much time on it, so let's use 30 minutes, and then you can go immediately to the results, and you will see that there is only 4 results left. If you want to go to the original source, we made a nice link to the original source, and this allows you to browse the data. If you now find in this subset interesting information that you would like to do further analytics on, you can basically save this subset into a new action with extra attributes or with new names and combine it with yet another query and make your model evolve. Since we don't duplicate, it doesn't matter how many times you reuse the values because they will be addressed by their ID behind the scenes. And you can then actually create a model that becomes very complex in certain areas and move from there. So this Explorer window is filled automatically when you bring data into the Dynizer. So this is typically, you add a number of sources, you can have a look here, you browse through it, and you see. So this is a combination of the very structured fields that you have with recipes. Who's the cook? How much time does it take? What do you need to have in your fridge to actually prepare it? With then an analysis of the text of the cooking instructions so that you can basically go. Very funny anecdote. We ask our kids on Sundays to actually cook for us. And typically that was a pretty difficult thing to motivate them, because yeah, what do we make? And you have no ideas. And so I thought, oh, let's try and solve two problems, because often they were asking me like, Daddy, what is this you're doing in your company? Can you explain it? And every time I tried to explain it in theory, it was a nightmare, because they lost their interest after 2 minutes. So I decided, well, if with the recipes, maybe that's simple enough as content, so I can try and explain them by that. So we made this little access point to a number of recipes, and so I showed this, and I have to say that now the one who is of service on Sundays, typically, well, they are pretty happy, and we ate the most strange recipes, because there is quite some strange recipes in this set, but they love it, because they look in the fridge and they look for a combination, and then they say, oh, we don't want to spend too much time on it, let's see what we can make. And we have never eaten the same thing on Sunday since, let's say, this is live for about a year now, I think. And so it's since a year that we have a very, very nice varying menu on Sundays. Is it always good? No, but it's always fun at least. And it allows me to have peace on a Sunday afternoon, instead of having to convince my children of cooking and finding something easily. So that's the very first step. Let's now go into a little bit more detail. How do you make a mapping if you have an existing database? How does that data end up in the Dynizer? How do you add data from unstructured documents? And for that, I need to actually move to another environment with other data. So this is an environment in which I actually brought together some data from court judgments. And a court judgment, just to give you an idea, a court judgment, it's, if I just, then you will see what. So this is a very simple query, very regular. So this brings me the original document. So this is a PDF document, and this is a judgment that comes from the court in Antwerp, which actually has some kind of a very weak structure. What will you find in the document? Well, you will find the presentation of the parties in the court case. You will have the presentation of the lawyers. You will have the reasoning of the judge. You will have the conclusion of the judge, and you will basically have the signature of the document and the metadata which is the roll number of the document, which is its unique identifier, the date of the judgment, and the chamber of the court in which the judgment was pronounced. So this is typically what a court case looks like. What do we do with this, or what can we do with this in our Dynizer environment? Well, pretty simple. What can we do? And I'll show that by means of my pipelines. And I could run this real live, but since we have not a lot of time to do that, I want to avoid waiting time. So I actually put the documents into the system upfront. How do you do that? Well, you do that by configuring a pipeline. And we have, as you can see here, we have structured data pipelines and we have unstructured data pipelines. So that means if you have data coming from a relational database, the pipeline works in a slightly different way than when the data comes from an unstructured source, such as these PDF documents. What is here on the screen is an unstructured data pipeline. And what does that do? Basically, this is a set of containers in which we run our NLP stuff and our artificial intelligence stuff to basically transform the document into a series of actions with who, what, where, and when components. But that's not all. So how does the process work? Well, you basically have the input, you have a configuration that tells the system, okay, this is the goal of the pipeline, and so on, this is the data. We take the PDF, we extract the text. And then there is a first step, which we call pseudonymize. In this case, since it is sensitive data, the courthouse asked us to extract all the information that was pointing back to individuals, companies, organizations, lawyers, judges, people that testified, people that acted as an expert in the text, so that that information is taken out. So we have, since we recognize who, what, where, and when, we can replace these elements rather easily by labels that remove the link to the individual person, but that actually conserve the semantic meaning of what was there. If there is a person that was as a party in the text, we will call that personal party 1. If a company was a party in the judgment, then we would call that a commercial party. And we give them an index so that the semantics of the content remain the same, but all references to the pieces that could identify the individual are removed. We detect also the language of the document. In this case, it will mostly always be Dutch, and well, we have judgments in Belgium, of course, in French, in German, and in Dutch. We basically identify the sentences, reduce the words to their base form, and then in the next step, detect components. We basically split into word groups. What can we do further then? When we have the word groups, we attach a component type, who, what, where, when, or action to it. We also generate a summary of each part of the text. We define a weight for the identified elements. We then put it all together in a structure and import it into the Dynizer database. Basically, to do this, we do not consider the document as a whole, but we structure the document into 4 specific pieces. And I will show you what that looks like once the data is in the system. So you've seen the original document. That is actually cut up into 4 pieces, which is basically, and now I can actually go to my history if I'm, no, it doesn't matter. I'll just do it here. I can just say, okay, title page. These are the 4 parts of judgment in this case. So we have the title page, we have the data about the parties, we have the motivation of the judge, and we have, finally, we have the conclusion of the judge, and we will have basically the data about the people that made the judgment and the place where it was made. So basically, you see these elements popping up here, and what you see is that between the smaller than, bigger than sign, you don't have individual names anymore, but it says party 1, party 2. It says RRN, which is the, well, basically you could consider it as a kind of social security number that uniquely identifies each Belgian citizen. You have an address and so on. So basically this is stored fully pseudonymized in the database. So there is, if you want to use this data, there is no way you can go back to the original names from this part of the data. We do that for every, so the motivation is, and you could say, okay, party data, that's relatively easy to do. If you go to the motivation of the judge, that's plain text, and you see here that's fully running text, and also there we do a number of replacements so that it becomes fully anonymized. This is quite a long part always. And so for that, we also, in the same go, we create a summary, which I will show you in a couple of minutes. And so basically, if we go to the conclusion, which is shorter, then we also see here that we nicely de-identify the stuff. So this is how you make the content of the documents. And you see here also that in the final part, there is no names, but it says there was one judge, there was one graphier, and that's about it. It just takes the date because that doesn't have to be removed. So this is a very nice system. You see here that we do extractions of the people and so on. So the names that we have, if you have access to the system, you can find out the names and the parties that were. So you can do all kinds of interesting analytics on the content of these documents. So this is how you add. If we now have, let's say, a table, for example, with data about all the lawyers in Belgium, you can add that to the system as well. For that, we have structured pipeline. So structured pipeline, you can see that here. The structured pipeline is a smaller and a little bit of a faster process, because basically you give it a configuration and it does the import. Now, what does a structured pipeline combine? It combines, obviously, it combines you the source. So in this case, if I just look at the source, this is a Postgres database that runs on my network. So here you have the link to the source. It's a JSON definition that you fill out. So you set the port, you set the address, and then you define your query. So this is just a select star from one table to keep it simple. That's the source. And then, of course, you need to have a mapping. And how do you make a mapping? Well, a mapping couldn't be easier. Basically here, you give it an ID, and then you have the mapping. You define the action to which you want to, or that you want to use to assign the data to. You then say, in my result set or in my table from my source, the first column, which is of type string, I map that to a component who, and I give it a label first name. Then I can say the second column, that's also of type string. I map that also to a component who, and I give that the label last name. And you do that for all the elements in your query or in your selected table. You run the pipeline, and that ends then up in an action that looks like this. And then you see here that you have, and this pretty much looks like a regular table in a relational database, except for the fact that every column here has a who, a what, or a when, or a where definition. And now comes the nice part, because this is in the same system. If I now do a query, I can actually write a simple query here where I can say, select, for example, the persons, the lawyers. Let me have a look here. The first name and the street as first name, last name, area code, city, from, and this is something that normally in a regular relational database does not exist, but it's completely in line with SQL syntax. From Dynizer, this goes over the full data model without you having to specify any action, any table whatsoever. And you say where, that's just your regular where clause, contains. You don't have to specify which of these columns contains the value that you're looking for. And I could say here, ankles. And I can use this name because the lady is a lovely neighbor and she gave me the permission to use her name in this demonstration. And now I see that from a judgment, I extracted all these people in the judgment that in which Mrs. Enkels played a role as a lawyer. And from the table advocaat, which comes from a relational system, I get more details about who she is. So she lives in a community called Schilde, which has the area code 2970. And so with this, you can easily, without having to know where in the model your data is, figure out everything that is linked to a specific person, to a specific city, to a specific set of elements, because you can combine and elements and what have you more. And so this allows you, what I would like to show you here, we only have 3 documents loaded in and a small table with a couple of records. This is just for demo purposes, of course. But the Explorer here, you see, it also exists here with the data extracted from the different sources. And you can do exactly the same thing as what I did in my Explorer window about the recipes. So this is basically my story for you today. Make it simple. I have nowhere in my data model defined any links. I don't know whether that has been noticed so far, but we don't have the notion of foreign key or primary key or what have you. The overlaps are defined by overlapping data elements. We typically in here, we use full overlaps. So the string value or the number value or the date value should be the exact same value, but we have the possibility to use functions to allow some deviation there. We could do, for example, a Levenstein distance on strings to actually have a broader set of matches if we wanted to. You can also define a range. If you say, oh no, it doesn't need to match on this exact date, but it needs to match on a range of dates or on a range of numbers, that's also possible. So this allows you to basically make very complex queries in a rather easy way, and to create a model that is rather simple to get started and that you can refine as you go, as you have more specific questions and so on. So basically, this is more or less my story for you today. And I hope that raised some questions or some remarks or what have you.
Yeah, thank you, Michael. That was great. I have a question, and also if anyone else has questions, please feel free to put them in the chat window. Have you had any suggestions about putting, instead of using SQL, maybe using another kind of query language such as Cypher, which is a graph modeling language where you could actually analyze the data and say, okay, here's one person, here's another person, what are all the ways they're related, or anything like that?
Yes, well, basically because the SQL has been developed based on the first query language that we defined, which was basically very much inspired by Cypher. We took the example of the Oracle graph querying language that they use in their spatial option on the database, and we actually modeled that. The trouble with that was that it works really fine, so we can actually provide that interface. But what we learned is that commercially, in a lot of cases, people prefer the SQL. But we can make well, it's not Cypher, or Cypher. It looks pretty much like that, and it is graph querying. But in all honesty, our actual customers prefer SQL.
Okay. Interesting.
And it would be much more intuitive, in my opinion, to use the graph way of doing things. But strangely enough, a lot of people still stick pretty much with SQL.
Okay. Thank you. Thanks, Michael. Any other questions? We actually are right on time, but we do have room for one more question if there's any other questions. All right. Excellent presentation. Thank you very much, Michael.
Thank you, Steve. And hope that people got something new out of it.
I definitely did.
Okay. Thanks a lot.
Great. Thank you.